In this video, we're going to talk about vector equations, parametric equations, and symmetric equations of a line in R3. First, let's determine the vector equation and parametric equations of a line that passes through the points A, 2, -3, 4, and B, 8, 1, -9. Well, we need a position vector and a direction vector. We'll get our direction vector first. If you recall, direction vectors are typically given the letter M to denote them. So direction vector will be whatever the vector is between A and B. And we can see that that will just be 8 minus 2, and then 1 minus -3, and then -9 minus 4. So we'll see our direction vector is actually 6, 4, -13. Then, since the point 2, -3, 4 is on the line, we can use the vector 2, -3, 4 to be a position vector. And so we've got a direction vector and a position vector, and we can state a vector equation of the line as shown. And of course, we remember to include our parameter, which we're calling t in this case. And we put a t in front of the direction vector. Now, since we determined the vector equation of the line to be r equals 2, -3, 4 plus t, 6, 4, -13, therefore we can say that a parametric expression for x is 2 plus t times 6. And parametric expression for y is -3 plus t times 4. And a parametric expression for z is 4 plus t times -13. And so we've got the parametric equations. Now, in this question, we want to show that the two vector equations shown below represent the same line. And just like in 2 dimensions, this is a two-step process. The first thing we want to do is show that the position vector for one line could be used as the position vector for the other line. So that just, we'll show you that in a moment. And the other thing we want to show you is that the direction vector for one line is collinear to the direction vector for the other line. And if we can show both of those things, then we will have shown that the two equations represent the same line. So we're going to first show that the two lines are collinear, which means parallel. And we can do this by just showing that these two direction vectors are scalar multiples. Well, since -9, 6, 3 is equal to -3 times 3, -2, -1, therefore the direction vectors are scalar multiples and the lines are collinear. Okay, well that's fine, but we also have to show that the position vector of one could be used as a position vector of another one. So we're going to recall grade 9 math. If two lines are parallel and share a point, then that means the lines are coincident, i.e. the lines are the same. We've shown them to be parallel, so all we have to do now is show that they share a point. Since the position vector 3, 1, 0 is used as a position vector for the first line, that means the point 3, 1, 0 is a point on the first line. Let's just show that it's also a point on the second line. So we ask that question, is it a point on the second line? Well, what we're going to do now is we're just going to let the parametric expression for x equal 3. And then we're going to let the parametric expression for y equal 1, and we're going to let the parametric expression for z equal 0. And if we get the same value for t for all of them, then we will have shown that it's the same equation. Or sorry, we will have shown that 3, 1, 0 is a point on the second line, and therefore that the position vectors can be interchanged. And I'm just recognizing here a little typo. It says z equals 3t. It should actually say z equals 3 minus t. We're missing a minus sign there. So What we're going to do then, like we said a minute ago, let 3 equal the parametric expression for the second line. And when you do that, you see that t ends up equaling 3. Then we're going to let 1 equal the parametric expression for the second line, and we're going to get that t equals 3. And then we're going to let 0 equal the parametric expression for z for the second line, and we'll get that t equals 3. So what that means is if I let t equal 3 in the second line, then a point on that second line is 3, 1, 0, meaning 3, 1, 0 is a valid direction vector for the second one. And since we've now shown both parts of the process, then we have shown that it is indeed the same line written just with two different equations. Okay, so here it is here. Since the lines are collinear and share a point in common, therefore the two equations represent the same line. Now, we're going to show that these two vector equations here represent different lines that are parallel. So what we're going to do now is show that the direction vectors are scalar multiples of each other, and then we'll be able to show that the lines are parallel. So we've got one direction vector here and one direction vector here. To show the lines are parallel, we'll show one is a scalar multiple of the other. And we see, yeah, the second direction vector is just -2 times the first one. We have collinear lines, we have parallel lines. Now, we're going to show that the lines, however, are distinct by showing there's a point on one line that's not on the other. Since -2, 2, 3 is a position vector for the first line, therefore it's a point on the first line, let's show that it's not a point on the second line. So what we do, just like in the last question, we're going to let -2 equal the parametric expression for x in the second line. We get t equals 1. We're going to let 2 equal the parametric expression for y in the second line. We get t equals 1. So far, so good. It looks like it will be a point on the line. But then we let z equal 3, and we plug that into the parametric expression for z in the second line. We get t equals 5/6. Pretty close, but different. So therefore, -2, 2, 3 is not on the second line. And what that means is therefore the lines are parallel, but they're not the same line. And in math, we say parallel non-coincident. Okay, so now we're going to ask if the line shown has a Z-intercept. And a Z-intercept will occur when the line intersects the z-axis, and points on the z-axis all have x coordinates of 0 and y coordinates of 0. So we're going to let x equals 0 and y equals 0, and then we're going to see if we get the same t value both times, and if we do, then we're going to determine the z value at that value of t. So letting x equals 0, we get t equals -2. Letting y equals 0, we get t equals -4. Different values for t. Therefore, there is no point on that line with the x value of 0 and a y value of 0. Therefore, there is no z-intercept. Okay? Now, this question here asks us to determine the y-intercept of the line shown. The way the question is worded, it has a certain degree of confidence that there is, in fact, a y-intercept. So we can, probably assume that there will be, and we'll get the same value of t, letting x equals 0 and z equals 0, and then we'll plug that in for y. But again, just like in the last question, if you have a y-intercept, then that means at that point x equals 0 and z equals 0. So that'll be our strategy. So we want to let x equals 0 and z equals 0, and in both cases solve for t. If we get different values, there's no y-intercept. If we get the same value, there is a y-intercept. So for x, we get 6 plus t times -3 will equal 0. That means t is 2. And for y, we get 5 plus t times -1 equals, or sorry, for z, I apologize. For z, we get -4 plus t times 2 equals 0, and that means t is equal to 2. So since there is a t value that sets x equal to 0 and z equals 0, that means there is a y-intercept. and it'll be at the point where t equals 2. So now we just have to take that t value of 2 and plug it in. We do that, and we get y equals 3. So x is 0, z is 0, y is 3, and we found our y-intercept, 0, 3, 0. Now, we're going to talk about a new type of line. This works in 3 dimensions, and it is called a symmetric equation. Just for a moment, suppose we're given a vector equation of a line in 3 dimensions. Looking at that, we would say that x is equal to x naught plus a times t. We'd be able to solve for t in that equation right there by subtracting x naught from both sides and then dividing both sides by a. And if we did that, we would have an expression for t. Well, similarly, we can do that for the y parametric equation. If y is equal to y naught plus at, then that would mean y minus y naught equals at. Sorry, that should be a b there. Right, y is equal to y naught plus b times t. So we would say, write that down. We would subtract y naught from both sides, and then we would divide both sides by b. We'd get y minus y naught over b is equal to t. And then finally, following the same procedure for z, z equals z naught plus c times t. Solving for t, we'd say z minus z naught equals ct, and z minus z naught over c is equal to t. Now, what has happened is we've gotten the same t isolated in all 3 questions. So all those t values are equal to each other, which means this x minus x naught over a must be equal to that y minus y naught over b, which must be equal to that z minus z naught over c. And that philosophy forms the basis for our symmetric equation of a line. So here we go, we'll show it typed out. X is x naught plus ta, y is y naught plus tb, z is z naught plus tc. We do the work we just did a minute ago. You can maybe freeze the screen if you want to see it. But we get t equaling x minus x naught over a, y minus y naught over b, and z minus z naught over c. Now, since t is equal to all those quantities, that must mean all those quantities must be equal to each other. So that must mean x minus x naught over a equals y minus y naught over b equals z minus z naught over c. So we can make a statement. If the vector equation of a line is this equation shown, then that means a symmetric equation of a line is this equation shown. But of course, since a, b, and c are all values in the denominator, we cannot let any of them equal 0. Okay? Now, what's kind of neat about this, if you'll notice, if you see an equation of a line written in symmetric form, right away you can say, okay, my position vector is x naught, y naught, z naught, and my direction vector is ABC, because you can just go back to that form. So that's pretty cool. So let's put this into use. We're going to determine the symmetric equation of a line that goes through the points 2, 5, 3 and 9, 6, 8. Well, let's let 2, 5, 3 be the position vector. Let's let the vector 2, 5, 3 be that. We know the direction vector will be the vector between the points A and B. So that direction vector will be 7, 1, 5. So the vector equation of the line would be 2, 5, 3 plus t times 7, 1, 5. Well, now that we have that, the symmetric equation of a line is simply x minus 2 over 7 equal to y minus 5 over 1 equal to z minus 3 over 5. And we write it out. And there's our symmetric equation. Now, if as you know, we don't normally write fractions with the denominator of 1. We'll often just, write, instead of y minus 5 quantity over 1, we'll often just write y minus 5. So a lot of times you'll see the symmetric equation of the line written that way. Well, let's do another example. The symmetric equation of a line going through 3, 6, 2 and negative 2, 6, 1. Well, let's use 3, 6, 2 as our position vector. And we're going to use the vector between the points 3, 6, 2 and negative 2, 6, 1 as our direction vector, and that vector is negative 5, 0, negative 1. Now, there's a convention in math. What we just said a moment ago is the direction vector of our line will be negative 5, 0, negative 1. There's a convention in math that we make the first non-zero component of the direction vector positive. What we're going to do here is we're going to multiply, instead of saying m is equal to negative 5, 0, 1, we're going to find a vector collinear to that has a positive x component. If we multiply negative 5, 0, negative 1 by negative 1, then instead of this, we can say that Rm will actually be 5, 0, 1. And we're allowed to do this because if you recall with direction vectors, we're multiplying the direction vector by the parameter t, which must take on all real values from negative infinity to infinity. So we can actually make the direction vector be anything collinear to the original direction vector, and it'll work out mathematically. We can't do that with a position vector, but we can do it with a direction vector. So we're going to say that our m is 5, 0, 1, and we'll say the vector equation of the line is 3, 6, 2 plus t times 5, 0, 1. Now you might be wondering, are you allowed to say, you might be wondering, are you allowed to say r is 3, 6, 2 plus t times negative 5, 0, negative 1? And the answer is yeah, you are allowed to say it, but again, it's like using proper grammar. There's a convention in math that you always begin your direction vector with a positive x component, so we like to follow those conventions. And if the x component is 0, then we make the y component be a positive. So we get our we get our vector equation of a line as shown on your screen. And now we might be tempted to say, okay, easy enough. X minus 3 over 5 equals y minus 6 over 0 equals z minus 2 over 1. And we might walk away there. But obviously, you can't have a denominator of 0. So the symmetric equation of a line has to be amended slightly when one of the components of the direction vector is 0. So when that happens, what we do is we simply say that this x minus 3 will equal this z minus 2. We get that part down. And then let's think about what it means for the one component of a direction vector to equal 0. If let's looking at the y's. If the y component of the direction vector is 0, then in the parametric expression, we're basically saying that y equals 6 plus 0t. Well, 0 times t is 6, so we're basically saying y is 6 and that it can't change. So we simply write that out. And so this becomes our symmetric equation. X minus 3 over 5 equals z minus 2 over 1, comma, there's a comma there, y equals 6. But again, just as we did before, we don't usually have a denominator of 1. So in this particular case, you would probably see the symmetric equation of the line written x minus 3 over 5 equals z minus 2, and y is equal to 6. Okay, well, let's see if we can state the vector equation of this line. And actually, just to show you, this is going to be pretty straightforward. Our position vector is going to be positive 4, negative 7, positive 11. Okay, and our direction vector is going to be 2, negative 2, 5. And t is an element of the reals. So that's going to be the answer that we see in a second. Okay, pretty easy to go from one version to the other. Now, what if we have a line as shown? Well, y plus 2 over 3, that's easy enough, y plus 2 over 3. To say equals z, Z is like Z minus 0 with a denominator of 1. So it's like saying y plus 2 over 3 equals Z minus 0 over 1. Okay? And then if we say x is equal to 7, that's like saying the x parametric expression would be 7 plus 0t. So that would mean that our direction vector for x has a component of 0. So putting all that together, if I had to write that vector equation, I would say, okay, for the position vector, my x component is 7, my y component is -2, my z component is 0. And then for the direction vectors, I would say that my x component of my direction vector is 0, and for the y component, it's a 3, and for the z component, it's a 1. Okay? And so this is a description of it all typed out, perhaps neater than we just did. The y component of the direction vector is 3 because that's the denominator of the y portion of the symmetric equation. The z component of the direction vector is 1 because that's the denominator of that part. You can just see it'd be z over 1. And the x component is 0 because the x portion is not included in the main part of the symmetric equation, but rather is alone at the end with a constant value of 7. So we see the direction vector to be 0, 3, 1. Now we see the position vector of x has a component of 7 because that's the constant value of x. The position vector has a y component of -2 because you switch the sign. And then the z component of the position vector will be 0 because to say z is like saying z minus 0 over 1. Okay? And again, putting that all together like we did a moment ago, we get the same answer we got a few minutes ago, which is that r is 7, -2, 0 plus t times 0, 3, 1. We should be saying t is an element of the reals at the end of this. I have a bad habit of forgetting to do that sometimes. Okay? Now, this next question is really interesting. There's a point on one line and a point on another line such that the distance between those 2 points is a minimum. We want to determine the coordinates of those 2 points. Now, the minimum distance occurs in such a way that the line from A to B will be perpendicular to both L1 and L2. So I want you to imagine that we've got 2 lines in 3 dimensions. These lines are quite possibly what we call skew. When you're in 3 dimensions, it's possible for 2 lines to not intersect and also to not be parallel. It's not possible in 2 dimensions for 2 lines to not intersect and also not be parallel, but it is possible in 3 dimensions. When that happens, those lines are called skew. But this diagram I'm drawing up at the top here is hard to do in 2 dimensions, but I just want you to imagine there's going to be a point on each line. On the first line, I'll call it A, and on the second line, I'll call it B. And there will be a point on each line and one point only, such that the distance between A and B can be shown this way, and such that that line from A to B will be perpendicular to the L1, which is right here. The equation for L1 is given here. And there's a point on L2, which is given by this equation here, where again the little line segment from A to B will be perpendicular to both. Okay, so how are we going to go about this? Well, using some logic, we know that since A is a point on the line L1, that A must have the coordinates 4 plus s times 1 for x, 2 plus -1 times s for y, and -1 plus -2 times s for z. Okay, since those are the parametric expressions for x, y, and z, that means that those are the coordinates of any point on the line. And similarly, point B will have the coordinates 0 plus t times 2, or in other words, just 2t for x, 1 plus t times 1, or in other words, just 1 plus t for y, and 3 plus t times 1, or in other words, 3 plus t for z. So what we've got here, we kind of know the coordinates of each of those points. And what we're saying, this is pretty ingenious, we're saying that the vector from A to B, so this vector that looks kind of vertical as I've drawn it, is going to have to be perpendicular to the first line, which means it'll be perpendicular to the first direction vector, which is M1. So the dot product there will be 0, and that this vector AB will be perpendicular to the second line, in other words, perpendicular to the second direction vector, which is M2, so that dot product will equal 0. So what we're about to do is pretty ingenious. We're about to come up with two equations, and those equations are going to involve both S and T. We'll have two equations with two unknowns. We'll be able to solve for S and T, and we'll get the coordinates of the points. It's pretty cool. So here we go. Again, we know the coordinates of point A are 4 plus S, 2 minus S, and negative 1 minus 2S. We're getting that from making the parametric expressions for that line. And we know the coordinates of point B, which is a point on this line, are going to be 2t, 1 plus t, and 3 plus t. And we get that by getting the parametric expressions of that line. And then what we do is we just determine what is the vector AB. And the vector AB is just going to be 2t minus the quantity 4 plus s. It's going to be 1 plus t minus the quantity 2 minus s. And it's going to be 3 plus t minus the quantity negative 1 minus 2s. We're just going to distribute these minus signs in. Pretty straightforward stuff. And we're going to evaluate, we're going to determine what is the expression for x, y, and z. And then we're going to do a little bit of simplifying. And when we do that simplifying, we're going to get the vector AB equal to this vector shown at the bottom of your screen. 2t minus s minus 4, t plus s minus 1, and t plus 2s plus 4. Now, like we said on the previous slide, that vector AB, which is this right here, that's got to be perpendicular to both the first direction vector and the second direction vector. And those direction vectors are pretty easy to find. The first direction vector is this one, and the second direction vector is this one. So all we have to do is take this vector and say that that vector's dot product with 1, negative 1, negative 2 is 0, and that vector's dot product with 2, 1, 1 is also 0. Okay, so let's do it finally. 2t minus s minus 4 times 1 plus and so when we do that, give me 1 second here. 4 plus, we get here 2t minus s minus 4. Sorry, let me just write this here. AB equals 2t minus s minus 4, comma, t plus s minus 1, comma, and t plus 2s plus 4. When we take this expression and multiply it by 1, and then add that to this expression multiplied by negative 1, and then add that to this expression multiplied by negative 2, we get this equation right here. And with a little bit of simplifying, we get negative t minus 6s minus 11 equals 0. And a little bit more simplifying just means t is equal to negative 6s minus 11. We've got one equation with two unknowns. Now what we're going to do in the next slide is we're going to dot it with the other direction vector. So we'll take this expression for x, which is 2t minus s minus 4. We'll multiply it by 2. and then this expression for y multiplied by 1, and we'll add it like we do at dot products, and this expression for z multiplied by 1, and we'll add it like we do with dot products, and we'll come up with a second equation. Okay, and when we do that, we get this, and so equation 2 tells us 6t plus s minus 5 equals 0. So now we've got equation 1 and equation 2, so we plug equation 1 into equation 2, and we get this expression. We get negative 71 equals 35s, so s is negative 71 over 35. And then t is equal to negative 6s minus 11. So that means t is equal to negative 6 times negative 71 over 35 minus 11. That ends up being 41 over 35. So what we now know is that we will have that those 2 points. One of them will be in line 1 where s equals negative 71 over 35. Plugging that into here, we get that the point will be right here, 69 over 35, comma 141 over 35, comma 107 over 35. And then we also get t equaling 41 over 35, and plugging that into here, we get that the coordinates of point B on line 2 are 82 over 35, comma 76 over 35, comma 146 over 35.